All right. So this is the video that's going to go with the problems that uh, many of the problems that we did just a few hours ago. It's still Tuesday, and it's 3:19 on the clock. So C block has ended about a half an hour ago, and we got through a bunch of these questions. I'm going to do them all. There's 12 questions here that I was hoping to get through, but again, laying out what differentiation and integration are not easy to do in 2 days. So, we're just talking about them. Again, I think it takes about 4 days of hearing something to just do some certain things mechanically, let alone to understand these two major operations in mathematics, probably the two most important operations ever devised in mathematics. Although the person who decided to put a triangle in a circle had to be pretty bright too. So Sir Isaac Newton, Wilhelm Leibniz, somebody in China, all were doing these problems around the same time historically. So let's get at it. So the first question that I asked was finding the minimum value of 2x squared minus 20x plus 7. Using calculus, going to find the minimum value, and we're going to try to justify why it's a minimum. So you pause the video at this stage, try the problem. Feel confident in knowing what to do with that already? Just move on. All right, so here we go. So y prime, 4x minus 20. We know we have a cup shape up, and the slope is equal to 0 at the vertex. This is what assigns slopes. So therefore, we want to know when it's 0, and we can see that x is 5. So I now know that x is 5 is the critical x value. How do we find the y value? We plug it into the position function. Sometimes this is referred to the parent function. The parent function. Okay, so this assigns slopes. And so the slope here is 0. Put in a 5, and you get 50 minus 100 plus 7. So the minimum value, the y value, that's all we want is the y value, there is minus 43. Now the question is, how do we prove that it's a minimum? Well, there's two ways to prove it. One is to sketch 4x minus 20, which is a linear function whose critical number is 5. We have a sign change there, negative, positive, and remember these are all slopes. If your slope is positive, you're going up. If your slopes are negative, you're coming down. So don't let that arrow fool you. You put your finger on the curve and you follow it from left to right. Y values are decreasing for all x values less than 5 and increasing for all values greater. So that's one way to prove that it was a minimum. The other way is to actually, and we didn't talk about it yet, the other way is to take the derivative of 4x minus 20, which is 4. It doesn't matter what the x is. If the acceleration is always positive, that means that your tangent slopes are always going up. So let's look at slopes of tangent that are always going up. Let's look at, let's stay with the quadratic. So maybe the slope at that instant is minus 10. And then maybe it's minus 5. And then it's minus 1, right? Slope of a tangent. So that slope is maybe minus 1. And then it's 0. And then it's positive 1. Then it's positive 5, going up at 5 to 1, going up at 10 to 1. So what are these slopes doing? Minus 10 to minus 5 to minus 1 to 0 to 1 to 5 to 10. On a number line, I started at negative 10. I ended at positive 10. I think the slopes are going up. If the slopes are going up, we get a shape that we call concave up. So this tells me, this second derivative, which is all about acceleration, tells me that I have a shape that is always concave up. At 5, I have a slope at 0. That's another way to show that it is a minimum. Now, what if it had been a slope that was negative? Always negative. Let's say that my second derivative is always negative. Let's say negative 2. What that means is that I have a slope that is going to give me a concave down shape because my slopes are always decreasing. So that might have been 10. That might have been 5. That might have been 1. That might have been 0. That might have been negative 1. That might have been negative 5. That might have been negative 10 for slopes of the tangent, right? Well, what are these numbers doing? They're always going down. If they're always going down, I have a concave down shape with a slope, some slope that is equal to 0. Then that's going to prove you got a max. That's one way. All right. That's called the second derivative test. And the one we did before when we were looking at the sign change at 5, that's a first derivative test. I'll be talking about these all term long, right? And I'm not really worried about you until we get to about a week or 2 weeks before midterm as to whether or not you understand these conversations, which means we're going to have them every day, hopefully every day, for another several weeks. So you have time to process. But if you want to get a jump on that, you go to YouTube and you go first derivative test. That's all you have to do. You type in anything I say and I'll try to write it down. You do first derivative test for finding max and mins. Go look at YouTube. You're going to have somebody else repeat what I just did for a different problem. Honestly, that's how you can really learn calculus in this class. Use YouTube, use what I tell you, use YouTube, use what I tell you, and that extra practice is going to solidify your understanding. All right. So that was that question. The next question I asked was, at its y-intercept, y equals, I gave you, I didn't actually do, I gave a different, my eyesight let me down. So it was actually 2x to the 5th minus 20x plus 7. 2x to the 5th minus 20x plus 7. Okay? So we're going to try to find the slope at the y-intercept. My pre-calc kids should know this without doing calculus, but maybe we'll make the connection here. So you got to do the derivative, which could have also been called dy dx, and the derivative is 10x to the 4th minus 20. And we know that the y-intercept is 0, 7. That's a location. That's a parent function. We need the slope at that instant. The slope at that instant at 0 comes from 10x to the 4th minus 20. So if I plug in 0 into 10x to the 4th minus 20, at the y-intercept, I'm going down at 20 to 1. In other words, it was here to begin with. Those two terms, I don't care what polynomial you're looking at, there's your line through the y-intercept. I mean, if you put a 0, you get a 7. And you're going at 20 to 1. All right, so that's that. So the equation was, if I really do it out full hand, then y, the tangent, why don't I say, what should I use for tangent here? Linearization. Why don't I do tangent line equal to, let's do that. Let's do TL. Tangent line is equal to minus 20, x minus 0 plus 7. Obviously, you didn't need to write x minus 0. All right, so that was that one. Then we wanted to do equation line tangent to 2x squared minus 20x plus 7. 2x squared minus 20x plus 7 at x equals 10. And so what we're doing right now is something called linearization. Fancy term for writing the equation of a line. And linearization is going to allow us to do a bunch of things in calculus. All right, so you're pausing the video. I'm just continuing. So first I got to find out where the heck I am. Where I am, what x value. So what do we got? 200 minus 200? Oh, that's nice. Plus 7. So I'm back at 7. All right, so 0 gets me 7. And I know that this is symmetric, so probably instead of going down 20 to 1, I'm probably going up 20 to 1. But let's find the derivative. The derivative is 4x minus 20. Oh, yeah, we did this one before. Let's put in a 10. Let's put in an x value of 10. 40 minus 20 is 20. Okay, so the equation of line tangent, the tangent line is equal to a slope of 20 through 0, 7. Yeah, so if we wanted to get a complete picture, we did this one before. So this one was start at 7, go down at 20 to 1, at 5, back up, that was negative 43. We can see the symmetry 0, 7, and down 20 to 1. We can see we're going over here at 10 because that's 5 units to the right, 5 units to the left. 10 gets me 7, sorry. 10 gets me 7. And now I'm going up at 20 to 1. So we can kind of get a feel for that's accurate because of the symmetry of what's going on. Now, if I wanted to actually check that, well, I'll do that on Monday. But the way we would have checked it is we would have put a 10 and a 10.001. We would have gotten a Y1 and a Y2. And if we had subtracted those, we would have had a 20 to 1 ratio come out of those table values. Okay? All right. Find the maximum for minus 2x squared. Minus 2x squared minus plus 20x plus 7. Now we're finding a maximum and proving it. Okay, so pause the video, you go do it. Unpause, here we go. So back to y prime. Y prime is minus 4x plus 20. Oh, well that equals 0 at x equals 5. So if we were sketching this, looking from local behavior to end behavior, we would have started at 7. We would have been going up at 20 to 1, but obviously it's concave down. It's always concave down. That means our second derivative is always less than 0. We'll find that later. And we want a slope of 0, and we found the x value 5. So what is the minimum or the maximum in this case? We got to put 5 into this function. That's 100, so 57. Right, I took a shortcut, right? That's 100. All I did was cut it in half and add 7. What allows me to cut it in half? This is always twice this and opposite. So when you add those two, you always get half of the middle term. It's a little shortcut. Okay, I can show you why geometrically sometime, but that's an algebra 2 class. All right, where am I? All right, so how do we prove that that's a max? Well, we could get the second derivative, y double prime. Y double prime of this is negative 4, which is always less than 0. So this is always concave down. This is concave up for a shape. Okay? When we change from concave down to concave up, we have a point of inflection. We will be studying that as we go along. So a point of inflection, when I think of an inflection point, I don't know, I always think of singing. My mother was a good singer. I'm a terrible singer. Oh, there was an inflection point at the top. Scale going up and then going down. I don't know. I don't know if that's true or not. All right, so next question. I should have had these all on the board and just move the camera. Oh, I should do it better. First time through, I'll get better. I'll get better. This time I actually checked the angle on the camera. So the next time I do that, I will remember. You'll see on every test, repetition is my friend. So I will repeat this the next time. And instead of looking like that, and hopefully I didn't miss much, you're looking like that. Now, I don't know. I'm going to have to go back and look at the video and see if I have been doing things at the bottom of the screen that haven't been able to be seen. If that's the case, I'll upload this anyway. I'll get through Thanksgiving, and I'll bust in here and do it again. At least the first 5 or 6 problems. All right, now we're looking at write the equation line tangent to y equals 2x to the 5th minus 20x cubed plus 7. And we're going to write the equation line tangent at x equals 2. And one of the non-calculus skills that I would like you to develop is to get a sense of what this graph looks like without calculus. Pause the video and try. All right, I'm unpausing. So this is really y equals 2x to the 5th plus 0x to the 4th minus 20x cubed plus 0x squared plus 0x plus 7. There's the tangent to the y-intercept. 0x plus 7. Well, that's y equals 7, which means at the y-intercept, my graph is flat. That takes care of that term. Now, when I put the number 1 in, who's more powerful? The negative or the positive? Well, if I put 1 in, I'm going down 20. If I put 1 in here, I'm going up 2. So this graph is going down from here. At what rate? Well, probably something like this. We go from 0 to more negative. Now, at some point, and I don't know where, so I'm going to get rid of the x-axis, this term takes over. That's your graph. Now, it's flat here, right? So if I put in a negative number, that's a real big positive. So actually, this is a negative. I put in a negative, it's positive. So it actually has to do this. Now, I don't think I included that. I think we did this one in C block. And I was really concentrating more on the calculus concepts versus thinking about this a little bit more, right? I put negative 1 in. That makes this up 20. Negative 1 brings this down 2. So I really went up 18 units from 7, which is probably more than I've drawn here. Okay, so this thing has 1 real root, maybe 2 more, maybe a couple of imaginary. We'd have to play with it from the pre-calculus standpoint. All right, I forgot what I asked. Oh, at x equals 2. All right, so x equals 2 is somewhere in here. Again, I don't know where this axis is. Okay, so 2 is probably here somewhere, right? So let's locate it. 2 to the 5 is 32 times 2, 64. I remember doing this in class now. I think I butchered it in B block, if we got to it there. So what's that? Minus 70. Boy, this stage of the day, I get tired. So 160 minus 64. 6, I don't usually have to do that. 15 minus 6, 96. Yeah, 96 and 64, yeah, okay, so that works. Boy, I get tired at this stage. Anyway, I can't even do simple math right now because I got so many numbers going through my head. Take away 60 takes you to 104 more 96, so that's right. And 96 plus 7, negative 96, sorry. Negative 96 plus 7, negative 89. I think I remember that number. Okay, so that's the position. Again, my brain misfiring took me a while, sorry about that. So what's the rate of change? Sure looks like I'm on the negative branch still. So we got to take a derivative, and the derivative is 10x to the 4th minus 60x squared, and 7's constant, so that we don't have to worry about that. We drop in a 2, I remember this now, 160 minus 240. So we're actually going down at 80 units to 1. So this sucker is going to go down a while longer. Right? Probably like that. Now, if I wanted to find that x value, we're not gonna, but I hope you have an idea of how to do that with calculus. Oh, we should find that x value with a derivative like this. It's good algebra practice. Let's find that x value, and let's find that one too, because I think that's a local maximum. So how do we find this x value? Remember, the slope there is what? 0. This defines slope. So we are now solving 10x to the 4th minus 60x squared equals 0. I got news for you. That's algebra 1. If you're having trouble with that, it's on you to take a look at what I'm about to do and make sure that you understand it, do it yourself. I have to find a way to isolate x. I cannot subtract those because they are not like terms. I don't see any geometry here that's going to help me. So I rewrite it as a product because that will isolate my x terms. All right, so how do I write this as a product? I take out what's common, 10x squared times what? Times x squared minus 6. Again, my brain is getting a little tired. That means I have 3 areas to worry about. One of them occurs at square root of 6. That's when this would start to go back up. And the other one happens at negative root 6 over here. This is actually not a max or a min. Why not? Because you're supposed to have studied this in your last class. And you should have drawn those things. At square root of 6, we get a sign change. At negative root 6, we get a sign change. And at x squared, we don't. When I put a number bigger than negative root 6 in, I get positive infinity coming out of this. Sign change, no sign change, sign change. When the derivative is positive, I'm increasing until I get to root 6. And then it's negative until I get to 0. But at 0, and we actually had a point of inflection here, concave down to concave up. At 0, I do not get a max or a min because there's no sign change. But then it decreases again until square root of 6, which means I'm always going down with, I guess, another point of inflection somewhere in here, where I go from concave down to concave up. This is called the first derivative test for concavity. Notice I'm throwing a lot out there. First derivative test for concavity. Don't be afraid to use that either. It's one of the things we're going to learn. I hadn't planned on talking about it this soon, but when I uncover something, I mention it. And so that's a pre-cal skill that I hope you're bringing into class, because the prerequisite is that you're bringing it into class. All right. I worked heavily on this with folks. The problem people had with this was figuring that out. All right? I did it as a difference of two squares. I can't tell you how many people on the last final exam I gave in pre-cal lost all their points because they couldn't factor this correctly. People could not, the people who had trouble couldn't factor that correctly. And another problem was folks couldn't factor this correctly. Didn't even think of it. Didn't even see that as 1 plus cosine x times 1 minus cosine x. So I am going to talk about that briefly right now. And if you feel good about your factoring of those, go forward on the video here. All right, so this is what's going on. 25 minus 4. The Greeks figured out that that difference could have been written as 3 plus 2 times 3 minus 2. Now, what is the number 3? Oh, I usually do 9 minus 4. That was memorization. 5 plus 2, 5 minus 2. So what is the number 5? It's the square root of 25. What is the number 2? It's the square root of 4. So what is the form for the difference of two squares as a product? The sum of the square roots times the difference of the square roots. So I can factor any difference that you give me. I can factor A minus B. And just to show you, 7 times 3 is 21. And 21 is 25 minus 4. Okay? So I could factor A minus B because I know that that square area came from the square root of A, that square area came from the square root of B, which means that if I do the square root of A plus, I'm getting tired, A plus the square root of B times the square root of A minus the square root of B, I am going to get A minus B because the middle terms cancel. So this is the way I chose to get. I got x squared and I got 6. So what I did a minute ago is I worked with their square roots, x and the square root of 6. So I wrote x plus the square root of 6. Nice, I can just change that. And x minus the square root of 6. And so therefore I can see where I get sign changes on graphs. All right, talking more than I said I would, but that's okay. It's early in the term, somebody might have just picked up something. Okay, next problem. write the equation line tangent to the sine function. I don't think we got to do this in period B. So there's your sine function. We're going to find its derivative right now. This is the derivative. And what does the derivative measure? Pause. Slopes of tangents. Let's draw a tangent right here. How would you say this function, the y values, are the y values increasing or decreasing here, and at what rate? I tried to draw something that looked like it's 1-to-1. Okay, so at x equals 0, I have a slope of 1 for the sine function. So I'm looking at y prime of the sine of x. And its slope appears to be 1. What's that one? Well, that's pi over 2. 1/4 of the way around the circle, I get a slope of 0. We'll call that pi over 2, 0. Halfway around the circle at 180 degrees, which is pi, it looks like I'm going, don't put that arrow there. Looks like I'm going down at 1-to-1, not up at 1-to-1, not 0-to-1. I'm going down 1-to-1. At 3 pi over 2, 3/4 of the way around the circle, 270 degrees. Here's your circle, 270 degrees. I know my sine value is -1, but what's the slope of the tangent? 0. And then I'm back, once around the circle, I'm back to where I started from. 2 pi gets me 1. So I had a 0 and a 1. Geez, I wonder what that curve is. Well, the prerequisite to coming in the class is you recognize it. That's the cosine curve. So what is the derivative of the sine function? The cosine function. All right, so therefore you should be able to write the equation line tangent to the sine function now. Here's the sine function, let's see what I put on the sheet, pi over 3. You should be able to find pi over 3 on that curve. This is 0, not drawn well. This is 2 pi. I guess that's pi. I guess that's pi over 2. Pi is 180 divided by 2. Yes, I guess that's 90 degrees for folks who are struggling. So what is pi over 3? 60 degrees. There's 90. 60 is right about here. I'm looking for that tangent line right there. I'm looking for the equation of that line right there, the tangent line. So what do I need? I need the position. I need to know the y value that goes with pi over 3. Now, I've never had a calculus class where I've had more than 2 or 3 people coming in that actually knew those values easily. Okay, which means I probably have to teach it. All right, so what is pi? Pi is the top half of the circle. What are you doing? You're breaking it up into 3 parts. Okay, so there's one chunk, and that means that we're looking at a 60-degree angle. So that's a half, that's √3 over 2, and that's 1. So what is the sine at pi over 3? That dot right there is pi over 3. It's 60 degrees. I'm at √3 over 2, which is approximately 0.87. √3 over 2 is approximately 0.87. And the biggest the sine function get is 1. So I'm trying to give you a little review for anybody who did not have a good pre-calculus experience in working with the sine and cosine function. So I now know that the tangent line that grandma at pi over 3, which is approximately 1.04, at an hour and 4/100ths of an hour from now, she is going to be located at 0.87 or √3 over 2, 0.87, not quite a mile north of the Vermont-Massachusetts border. We have located grandma on Route 91. So let me erase this and get an exact answer. I need the slope. The slope comes from, we just proved the derivative of the sine is the cosine. We didn't prove it, but we kind of infer that it is at this point, into that it is. I will formally prove it at some point. Y prime cosine x. Oh, well, the cosine is just the width in the unit circle. So that's going up in a 1-to-2 ratio. Does it look like if this is 1 to 1, does it look like that's a little flatter? Not the greatest drawing, but it's less than 1. Very believable. Okay? So guess what you get to do on Monday? Write the equation of a tangent line to a sine function. Okay? We're going to do it every day. It's going to be on every test. All right. So we got to learn how to get these values. If you haven't learned in your last class, I know I'm not worried about my youngsters coming in. I feel pretty good about them doing that. We'll see how everybody else does. We spent a lot of time on it. We did one every day, the whole term, pretty much. 2 to 5, 2x plus 10 dx. We've been doing mostly derivatives. Now we're doing integration. What is integration? Integration is finding the area under a curve. These are called the limits. In this case, that's A to B. We are going to find the area under a curve from A to B. Now, obviously, fx is not that curve. Okay? But the way we find that is to use layers. That's going to represent a layer, and that layer has height. The height is using the x value in the calculation, and that is dx right there. So really, we've created a rectangle. It doesn't look like a rectangle. I'll make it a little bigger. Okay, let's blow it up. That's a rectangle. And so Tanner asked a great question. What happens to dx in this calculation? Well, isn't f of x just height? Or we'll call it length. Isn't dx just width? And I answered with length times width equals area. And I countered with what happened to w. Okay? It's not a sufficient answer for now, other than it gets involved in a part of a calculation. Now, for me to show you those calculations, we got to go further into the class than this, right? Where I will build up those calculations for you and show you. We're almost ready to do it, but there's more important things to try to get down. And that is some of the basics of the mechanics of integration, so that when I talk about it conceptually, it'll make more sense. So this is called, let's hold that, Tanner, if you watch this, let's hold that in abeyance. That's the word abeyance for your SATs. Abeyance is, we're going to look at it later. It's right now, it's on deck. You're going to get to the plate later. Okay, you're in abeyance. You're waiting for your turn. Okay. So you can think of it right now, I think, as transmission of the virus. So let's say the virus is being transmitted at a rate of 2x plus 10. Oh, no, that's not the analogy I did in C. In C, I made a different one. Okay? I'm saying this is a rate. Think of this as rate times time, and that's going to give us some kind of distance statement over here. And what I'm really saying is that came from a parent function. This is the rate. And we've just started talking about how do I go from the rates back to the parent function. And derivatives, we said, ax to the n, we do what? We multiply, and then we subtract 1. So the derivative of ax to the n is an x to the n minus 1. That's just the mechanics. And this is the easiest derivative we might take. Okay, so in other words, if I took the derivative of 5x to the 7th, I would get 7 times 5, 35x to the 6th. If I looked at the area under this curve, I would go 35x to the 6th. I would add 1 and divide by that number. And if I do that, 6 plus 1 is 7 into 35 is 5x to the 7th. And you can see how I can go from little f to big F and big F to little f. So we're trying to learn just the mechanics of that. All right, so how do I get from little f, which is 2x plus 10. That's little f right here, to big F. Well, what did 2x come from as a derivative? Well, we've talked about that, x squared, right? Check it. Multiply and drop 1. You get that. Constant rates come from linear functions. And I'm going to do this from 2 to 5. All right, now let me give you the physical context that I thought of in C block. And I don't know in B block if we got to this because that's 2 hours ago. And I can only remember 20 minutes times anything that 20 minutes ago, I can't remember. Well, maybe I can because this is a little bit more than 20, but an hour ago, oh, I'm struggling. There's a nursing home up in Vernon. It's only about 7 miles north. I'm headed there. All right, so what I thought of, if I thought of 2x plus 10, when you put 2 into that, you get the number 14. When you put 5 into that, you get the number 20. So I was thinking of an Olympic runner running a 100-meter dash. After 2 seconds, up to 14 yards per second. I had the wrong, I said 14 miles per hour or something, C block, but tired. So you would be doing about 14, yeah, this is actually good, 14 yards per second. Okay. So if this is 14 yards, if this is in yards per second, that rate, this is a rate. This helps. Putting some units in here actually helps right now. So this rate is yards per second. dx stands for seconds in this case. So I'm doing length, right? If I graph 2x plus 10, then I'm putting seconds on the x-axis. I'm putting yards per second on the y-axis. And there's your 2x plus 10. What happens when I make a rectangle? The x-axis is in seconds. The y-axis is in yards per second. And what happens to yards per second when I multiply by seconds? Woo, I get yards. Okay? So C block, I apologize for talking about hours and miles, but I'm trying to cram in some thoughts so that we can get to a worksheet Monday and Tuesday next week. Give you a chance, take your time at the board, talk to your peers. I come around, we start talking about it. And we can't get there to the point where you learn when you engage with the material until I throw a lot of stuff out there, which I'm doing right now, okay? So I'm looking at this worksheet and what we've talked about in class, and I got a feeling I can make a cracker barrel worksheet of about 20 problems that we get to work on a little more slowly, okay, for at least half the class. And the other half, throwing more stuff at you. All right, so back to a little bigger drawing. 2x plus 10, right there. There's the number 2 seconds. And here's 5 seconds. And so what does that area represent? Rate. This is the rate. This is time. Rate times time. This area under the curve is telling me the distance that Olympic athlete, that male or female athlete ran between second number 2 and second number 5. So I think that if we had a stopwatch on, we probably could say where the person is at any moment, right? We could run the tape back and go, oh, at 3 seconds, look at that runner go, 40 yards, oh, 40 meters, sorry, I'm dating myself. It's a 100-meter dash now. My dad was 100-yard dash. All right, so we got to compute this. All right, so how do we compute it? Well, it's right here. We want to know where the runner was at the 5-second mark. I like to do this. So at the 5-second mark, we drop it in. 5 times this is 25 plus 50. Oh, on the position function, at 5 seconds, we got ourselves 75 yards have been run. Somebody ran 75 yards. Very good. over this entire interval, the rates are positive, so I know I have a concave up shape, by the way. Oh, yes, person's running faster. At 2 seconds, 2 times that is 4, 2 times that is 40, 20. Boy, is this brain tired. 2 times 10 is 20. And so where am I? I'm at the 2 second mark would be right about there. And at 0, I'm here, obviously, the start of the race. And so 75 minus 24, there's 24. Put that in the wrong place. Repetition will be my friend as we go along. Oh yeah, that son of a gun is speeding up. Woo! Of course, there's got to be a maximum sprinting speed, so we'll just stop right there. Okay, is the person going faster at the 100-yard mile? Probably not. It's probably not reflective. It probably gets up to top speed and then kind of levels off. But anyway, this would have said that that area would be 51 units. All right, so, it kind of looks like a triangle, doesn't it? 3 units of change. Or trapezoid. It kind of looks like a trapezoid right there. Let's do a trapezoid. Let's do a quick trapezoid. The width, 1 trapezoid. I'll put this up a little. No, I can't put it up because it's concave up. So that height is, that height was at 2, 14. So this height is 14 at 2. Going back to the rate function. No, I want 2x plus 10. I said that, but I didn't go to that drawing. 2x plus 10 is a trapezoid. So here's 2x plus 10. So at 2, that's 14. At 5, that's 20. And a trapezoid is the width, which is 3 right here, divided by 2, because a trapezoid is the average of a left and a right rectangle. So it's the average. So 3 divided by 2, first altitude on the left, 14. Second altitude on the right, 20. So this is 34. Cut in half is 17. 17 times 3 is 51. And it had to be the same because that is an actual trapezoid here. Okay, so it had to come out to be the same. 51. What does that 51 represent? How many yards the Olympic athlete covered between moment 2 seconds and moment 5 seconds? All right, so we're already applying things to a given physical situation. Okay, getting there. Now we are going to do 2. I got to see when I started this so I might have to upload this to my web page. It's taking a lot longer to do this than I thought. But you got 5 days to look at it and start thinking about this. And really, all you got to do is watch it, 10 minutes a day or something to get something out of it. All right, so the next question. No more talking, I'm just doing. I'm tired. So 2 right-hand rectangles, square root of x. From x equals 1 to x equals 9. So I graph the square root of x. I go from 1 to 9. I want to approximate this with right-hand rectangles. I need the one in the middle. Right hand is this. And that overestimates. I'm using the right sides of the rectangles. To find this, you do the width, which is 9 minus 1, divided by the number of rectangles. In this case, it's only 2. So this is a width of 4, which means that has to be 5. 1 plus 4. So I need the width times the altitude on the right. What is that altitude on the right? At 5, what is this height? Well, it depends what the calculation is. Calculation is the square root of x. So that's the square root of x, or the square root of 5. This one over here is the square root of 9. So it's 4 times the square root of 5 plus 4 times the square root of 9. That gives me area 1 and area 2. And it's an overestimate because up here is error. And you'd have to do that on a calculator. I don't know the square root of 5 offhand. I'm going to guess it's about, I could do linearization in calculus and get within 1,000th of a decimal place. We're going to do that probably next week. I don't know what it is. Do it on your calculator. We could approximate. Nah, I'm not talking anymore. That's how you do that problem. Okay. Is it bigger or smaller? I said that. Write the equation line tangent to the sine x at x equals 7 pi over 4. Now, the reason I put it here on the worksheet is we did it a little while ago, and I like to have you forget what we talk about and then find out if you can remember. right? Because that means you're not memorizing for a test. You're actually learning and showing that you can handle something coming at you from all different directions, which is what math does at the higher levels. So can you draw a sine x? Hope so. What we had before. Where is 7 pi over 4? Oh, I know that's pi. I know that's 4 pi over 4. I know this is 8 pi over 4. That means this is 6 pi over 4. I guess I'm in the middle. I guess I'm right there. What is the sine of 7 pi over 4? Top half of the circle broken up into 4 parts. That means the bottom is broken up into 4 parts. Terrible drawing. I'm going to do it again. I'm just tired. Okay. That's a little better. Okay, the sine is that altitude. That altitude is a y value of negative root 2 over 2. Hopefully you've done enough that you followed that very quickly. And therefore, the tangent line, I'm going to do TL from now on, x minus 7 pi over 4. So 4 goes into 3.14. I don't know, 78 times 7. I don't know, 79. I don't know. Sometime in the future, grandma is south of the border minus root 2 over 2, which is minus 0.71. So she's just less than a mile south of the border between Mass and Vermont. And the cosine gives us the cosine is the width. What's the width at 7 pi over 4? Root 2 over 2. So there's your equation of the tangent line. That's what you're going to have to do for me before midterm. Show me that you can do that. Some of you are going to have to learn how to figure out the sine of 7 pi over 4, how to draft the sine. You're going to have to do what you should have done last term. Okay? And that you can do by coming to math help on Monday nights or Wednesday nights. Yours truly does it from 7 o'clock to 9:45. And if you don't know how to get the sine of 7 pi over 4, when I did that, you should be coming. Okay, you should be coming. Because you can't take rate functions unless you know how to draw and understand the position functions. Okay, so a lot of you are going to have to come and learn how to graph ln of x, learn what it means, what it's about, and don't be afraid to do so because you can do it, but you're going to have those conversations. Okay, so I'll pose the question. Do you know what the ln of x is finding? If you don't have an answer to that, think about Monday night and Wednesday night math help. All right. Next question. Almost done. We're almost done. Mechanical questions. Very good. 4 more questions. Integrate 3x squared dx. What do you get? Well, you're supposed to add 1 and then divide by that number. So what is that? 3 into 3 gets us x cubed. Yes, that's big F. What's little f? 3x squared. There's a relationship here. And you actually have to put a c there. Because the derivative of x cubed plus any, I don't care what number you put here, 99. That's big F. What's little f? 3x squared. This could have been 999. Derivative of a constant is 0. Okay, so this is called an indefinite integral. Indefinite. Okay? And I hope that, you might start thinking about the sleeves I've been putting on the cube in class. 3 squares and a little bit of thickness. 3 squares and there's your little bit of thickness. Layering process. All right, then the next question is, what happens if I go from 1 to 3? Well, that's called a definite integral. That's like how far did the runner run from second 1 to second 3 if that was his rate or her rate. So we write big F, that's big F right there. We anti-differentiate, it's called sometimes. Go in the other direction. And we do it from 1 to 3. Those are the limits of integration. So I am now looking at 3x squared, and I'm looking at the area from 1 to 3. I'm looking at that area. This calculation is going to find it for me because I'm going to find out what the volume is at 3, 27. What the volume is at 1, 1. So that answer is 26 units of area. Now we're going to try to go back and forth from big F to little f. Okay, so we're going to go from, we're going to integrate 6x squared minus 8x plus 9. What does it mean to integrate? It means the summation symbol, dx, adding up all those slivers of area under that curve. All right, so that's big, that's little f. I want big F now. Big F, you take your time. I'm going to do it quickly. 2x cubed minus 4x squared plus 9x plus c. Now I'm going to go back to little f. How do I go back to little f? Oh, 6x squared minus 8x plus 9. Now I'm going to integrate. How do I integrate? Up 1 and divide it in. 3 and a 6, 2x cubed. 1 plus 1 is 2 into negative 8, negative 4x squared. Constants, slopes come from linear functions, plus c. Hopefully you can see that we're going from one to the other and back and forth, inverse operations. Kind of a complicated one, but mechanically that's what we're doing. Okay, let's look at the next problem. All right, next problem. Last one. We're going to look at the accumulation of area under the cosine function, pictorially. We're not going to do it mechanically. We're going to look at it pictorially. So do you know, and we'll start from 0. And we'll go to some destination to the right. We're only going to look at the positive side of the x-axis. Well, you got to be able to graph the cosine curve. Because this is all about the area under the cosine curve. And whatever this x value is, that strip of area, the height is the cosine of that x value, and the width of that little strip of area is dx. And if I add up a whole bunch of them, it starts to look like this. There's my first strip of area. Okay, I'm looking to the right. That means my width is a positive width. If I look to the left, it's actually negative. x2 minus x1 be negative. All right, and I'm looking up, and the height is the cosine of whatever x value I'm picking. All right, so I'm going to start drawing some accumulation. My area is doing what? It's accumulating. The height's positive, the widths are positive. So I know I'm going up. But how am I going up? Each strip is what? Each height is a little smaller than the preceding one. Smaller and smaller positive values until I get to right there. And then I get a sign change. So I was accumulating area less and less quickly until I got right here. My widths are still positive. My widths are always going to be positive because I'm looking to the right. But what kind of heights am I getting? I'm getting negative. So I'm getting negative amounts right now that are doing what? More and more negative. Each strip of area is more and more negative. So if I add each of those up, I'm going down until I get to here. Because I'm still going down. These strips are still negative. That's a negative altitude, a positive width. That's a negative altitude, right? Each of these, obviously I'm doing all the strips in between, right? Thousands of Riemann sums, thousands of rectangles. But each one is less negative than the preceding one. That means I'm still going down, just not as quickly. And then I get to a sign change where I'm not going down anymore. I'm actually starting to do what? I'm going up more and more quickly until I get to here again. Then I start to get another branch of that. So what are we looking at? There's one period. I hope you recognize the sine function. So what is the integration of the cosine function? Sine function. And this is an indefinite integral because I really didn't, let's get rid of these now. That's an indefinite integral, so plus c. What's the derivative of the sine function? Because this is big F. Derivative of the sine function is the cosine function. Oh, so this is the rate of that. And this is the amount function. And how do I take a derivative? I memorized this one. Derivative of sine is cosine. So that is now part of our lexicon. All right, we will be finding the derivatives of everything you work with. All right, how do we find immediate rate of change? Now I'm going to close this and try to see if I can upload it. And if I can't upload it, I go upload it to my YouTube channel, and then I can put it on Canvas. Okay, so that took a lot longer than I thought, but hopefully it's useful. My God, I think I went almost an hour. Oh, tired brain. All right, everybody have a great Thanksgiving. Stay safe, keep the masks on, keep the social distancing. This is not something to fool with. You are young. That doesn't mean you can't get seriously ill. Less chance of it, obviously, but you got people in your life I hope you care about that you don't want to get sick. So let's stick together, keep the masks on, keep the distance. And on Monday, I'm pretty sure we're in room 108, which is where I am now. This is a much better room for us. 2 whiteboards there, 2 whiteboards there, 2 in the front. Ah, God, we don't have 12 people in either class that are here right now. We can put 2 people over there, a couple people there, a couple people there. If you know somebody in the class, if those of you who are looking at this remotely, who are taking the class remotely right now, if you can email somebody that you know in the class and you want to work with, you know, copy the link. I don't know how that works. They use my link. I don't. You guys are the technological geniuses, right? This is the old guy. I just know where to turn the button on for the computer is. So if you can sort out how to FaceTime or whatever, join the class with somebody whose camera is on me, or you can join them. I'd like to have you folks who are learning remotely not all gang up to one place. I want to have you have a chance to actually give input. So I'd like you to work with a pair of people. And so when we do the problems on the board, you have a chance to chime in and go, hey, I think that's wrong, or I think that's right. That's what I got. That's not what I got. All right, very important that you talk through the concepts, that you try to talk through the concepts, because you got to put them in some working order, and that's going to take time. That's going to take time. And right now, we are in the 2-week, probably the first half of the term is going to be loading up on you. We might not be able to get all the concepts done. So what I'm looking for is the tail that wags the dog, right? So you're walking this way into uncharted territory, but behind you is the happy tail saying, oh, 4 days ago, I couldn't do that. Now I can, okay? And as we move in that direction, oh, yeah, woo, you're accumulating knowledge, okay? So this class is an accumulation function. I am integrating the heck out of you. Very good. See you on Monday of next week. Bye-bye.